Every German aviation documentary celebrates the Junkers Jumo Ta-152 as the advanced engine that powered the Focke-Wulf Ta-152 and late-war FW190D variants to legendary performance. Its two-stage supercharger and fuel injection represented cutting-edge technology that Allied engineers studied obsessively after the war. But declassified production records reveal a different story. The Jumo Ta-152 arrived 2 years late, suffered catastrophic manufacturing problems, and achieved performance specifications only under test conditions that combat operations never permitted. This wasn't the war-winning powerplant German propaganda claimed. By 1942, Germany's aviation industry faced a crisis that threatened the entire Luftwaffe fighter program. The Junkers Jumo Ta-11, powering everything from Ju-87 Stukas to early FW190 variants, was obsolete. Allied fighters climbed higher, flew faster, and outperformed aircraft using the aging inline engine. Junkers engineers had been working on a replacement since 1939, but development dragged as resources flowed to other programs deemed more urgent. The Jumo 213 design promised revolutionary capabilities: 35-litre displacement producing 1,750 horsepower at war emergency power, two-stage supercharging maintaining performance above 30,000 feet, and direct fuel injection providing smooth power delivery at any altitude, specifications that would have made it superior to the Rolls-Royce Merlin and Allison V1710 engines powering Allied fighters if the promised performance actually materialized in operational aircraft. The delay proved catastrophic. Original specifications called for the Jumo Ta-153 entering production in 1941, giving Germany a significant performance advantage during the crucial Battle of Britain period. Instead, development problems pushed the timeline repeatedly. Supercharger design required constant revision. Cooling systems proved inadequate. Crankshaft failures plagued early prototypes. Each delay meant another year of German fighters operating with underpowered engines, while Allied aviation caught up technologically, and by the time production finally began in late 1943, the Jumo 213 specifications no longer represented a revolutionary advantage, but merely competitive parity with engines Britain and America had been producing for months. The Reich Air Ministry demanded immediate deployment, regardless of development status. Frontline squadrons needed better engines immediately. Quality control concerns were secondary to operational necessity. This decision, prioritizing quantity over reliability, would haunt the Jumo Ta-153 program throughout its operational life. But the replacement brought problems worse than what it solved. On paper, the Jumo Ta-153 represented engineering brilliance. Its two-stage, three-speed supercharger could maintain sea-level power output at altitudes where single-stage designs gasped for air. The fuel injection system used high-pressure pumps, delivering precisely metered fuel regardless of G-forces or aircraft attitude. Sodium-cooled exhaust valves transferred heat 3 times more efficiently than solid steel. The cylinder head design incorporated 4 valves per cylinder decades before this configuration became standard in automotive engines, allowing superior breathing characteristics that maximized volumetric efficiency, while the crankshaft used advanced nitriding processes that hardened bearing surfaces to resist wear under sustained high-power operations that combat missions demanded. But Germany couldn't produce the materials these advanced designs required. The Reich's strategic situation in 1943 meant critical alloying elements were unavailable in sufficient quantities. Chromium, essential for high-temperature steel alloys, came primarily from Turkey and the Soviet Union, neither source reliable. Nickel supplies had been exhausted. Molybdenum reserves were nearly depleted. Engineers were forced to reformulate every material specification, substituting inferior alternatives that couldn't withstand the stresses the engine was designed to handle, creating fundamental contradictions where advanced engineering demanded materials that strategic reality couldn't provide, dooming the design before a single production engine was assembled. The supercharger system suffered most severely. Turbine blades spinning at 20,000 RPM, while subjected to 600 degrees Celsius exhaust temperatures required special alloys. Germany had to use mild steel with protective coatings that flaked off after hours of operation. Bearings designed for chromium steel ran on inferior substitutes that wore rapidly. Connecting rods specified for forged aluminum alloys were manufactured from castings that cracked under sustained load. Quality metallurgists who understood these compromises were conscripted to frontline service or arrested during Gestapo purges of anyone questioning official production targets, leaving factories staffed by technicians who followed specifications without understanding why certain materials were critical or what failures the substitutions would cause. Yet even perfect specifications meant nothing when production began. Junkers facilities assigned to Jumo Ta-152 production operated under conditions that made quality control impossible. Allied bombing had destroyed primary factories, forcing production dispersal to dozens of smaller facilities hidden in forests, caves, and underground complexes. These improvised factories lacked precision machine tools, proper ventilation, adequate lighting, and temperature control necessary for maintaining the tolerances measured in 10,000ths of an inch that high-performance engine assembly required, yet production quotas demanded these facilities match output rates that peacetime factories with ideal conditions had struggled to achieve. Slave labor replaced skilled German machinists conscripted into Wehrmacht service. Concentration camp prisoners, Soviet POWs, and forced laborers from occupied territories assembled precision engines without training, tools, or motivation. Prisoners deliberately sabotaged production when possible, installing components backward, omitting critical fasteners, scoring bearing surfaces with abrasives, filling oil passages with metal shavings that would circulate through the engine during operation and destroy it within hours, acts of resistance that quality inspectors working under impossible quotas couldn't detect even when they tried. Assembly procedures that required hours were compressed to minutes. Torque specifications were ignored when proper tools weren't available. Critical measurements were estimated rather than verified. Inspection stamps were applied to engines that had never been tested because testing required fuel that didn't exist. By late 1944, approximately 40% of Jumo 213 engines failed acceptance testing. But production quotas forced their shipment to combat units anyway with documentation falsified to show they'd passed inspection, meaning Luftwaffe pilots were flying engines that manufacturers knew were defective but shipped because admitting quality problems meant execution for sabotage. The final assembly facility near Dessau operated in conditions bordering on medieval. Workers assembled engines by candlelight during power outages. Winter temperatures inside unheated buildings froze lubricants. Summer heat warped precision components before installation. The engines that reached squadrons carried deadly secrets inside. Luftwaffe propaganda published Jumo Ta-152 specifications that bore almost no relationship to operational performance. Official documents claimed the Jumo Ta-152A produced 1,750 horsepower at war emergency power with methanol water injection. Captured engines tested by Allied technical intelligence documented actual sustained output of 1,320 horsepower under combat conditions, a 25% specification inflation that misled German pilots about their aircraft's capabilities, while designers planned tactics assuming performance that engines couldn't deliver, creating dangerous gaps between what pilots expected and what their aircraft could actually achieve during combat engagements. Altitude performance specifications proved equally fraudulent. Published data indicated full power maintenance to 32,800 feet with the two-stage supercharger engaged. Operational testing showed severe power degradation beginning at 26,000 feet, with combat effectiveness essentially eliminated above 29,000 feet. FW-190D pilots briefed to intercept high-altitude American bomber formations discovered their engines couldn't maintain combat power at altitudes where mission planning assumed full capability, forcing them to abandon intercepts or risk engine failure during climb attempts that exceeded what their power plants could sustain. Fuel consumption rates published in pilot manuals understated actual operational requirements by approximately 35%. The discrepancy stemmed from test conditions using high-grade aviation fuel that combat units never received. By 1944, German aviation gasoline quality had degraded catastrophically as synthetic fuel plants struggled with damaged equipment and material shortages, producing 87-octane fuel when engines were designed for 96-octane minimum, forcing pilots to reduce power settings below specifications to prevent detonation that would destroy engines within minutes. Reliability specifications existed only in fantasy. Official overhaul intervals claimed 300 hours between major maintenance. Actual mean time between failure averaged 47 hours in combat operations. Luftwaffe maintenance records from Jagdgeschwader 26 show their FW-190D9 fighters equipped with Jumo 213 engines averaged one catastrophic engine failure for every 4 combat sorties during January 1945, creating situations where squadrons lost more aircraft to mechanical failures than to Allied fighters. Pilots discovered the specifications lied about more than just power. The Jumo 213's most celebrated feature, its two-stage, 3-speed supercharger, became its greatest liability in combat operations. The system promised to maintain sea-level power output at altitudes where Allied bombers cruised, finally giving German interceptors performance advantages at operationally critical altitudes. The supercharger system worked beautifully on test stands running optimal fuel at precisely controlled temperatures, but combat conditions involved rapid altitude changes, violent maneuvering, fluctuating temperatures, and sustained high-power operations that exposed fundamental design flaws the test regime never revealed, creating equipment that performed perfectly in laboratories but failed consistently during actual combat missions. The supercharger's 3-speed transmission required pilots to manually shift between low, medium, and high blower settings based on altitude. Shifting too early meant insufficient boost pressure and power loss. Shifting too late risked overboosting and catastrophic engine failure. German pilot training by 1944 consisted of perhaps 30 flight hours before combat assignment. Barely enough time to master basic flight controls, much less the complex engine management that the Jumo 213 demanded, meaning inexperienced replacement pilots were attempting to operate sophisticated power plants while simultaneously engaging veteran Allied pilots flying simpler, more forgiving aircraft. The intercooler system that cooled compressed air between supercharger stages created additional failure points. Coolant leaks were common. Radiator damage from combat meant immediate power loss. The entire system added 340 pounds compared to single-stage designs, weight that degraded the FW-190D's renowned handling characteristics and reduced performance advantages the heavier engine was supposed to provide. creating situations where the advanced power plant's weight penalties negated its power advantages, leaving aircraft that handled worse while performing no better than earlier variants with simpler engines. Temperature management became impossible during extended combat. Pilots reported chronic overheating during dogfights requiring sustained high power, but altitude problems were nothing compared to what fuel shortages created. By the time Jumo 213 production reached meaningful numbers in early 1945, strategic circumstances had eliminated any possibility of the engine affecting the war's outcome. Germany produced approximately 10,000 Jumo 213 engines during the war, impressive until compared to the 168,000 Merlin engines Britain produced or the 450,000-plus engines American factories delivered. The numerical disparity meant that even if every Jumo 213 performed flawlessly and every German pilot possessed superior skills, the sheer quantity of Allied aircraft would overwhelm Luftwaffe defenses through attrition warfare that technological advantages couldn't overcome, proving that engineering excellence without industrial capacity produces magnificent machines that lose wars to adequate equipment produced in overwhelming numbers. Fuel shortages crippled operations more effectively than any Allied fighter. Luftwaffe squadrons in March 1945 possessed combat-ready aircraft equipped with functioning Jumo 213 engines, but lacked fuel for training flights, combat missions, or even engine testing. W-190D fighters sat hidden in forest clearings, fully armed and mechanically sound, unable to launch because fuel reserves were reserved for a final defense that never materialized, creating the surreal situation where Germany's most advanced fighters became expensive lawn ornaments guarded by ground crews who had fuel for their vehicles but not for the aircraft they maintained. The training crisis proved equally devastating. Experienced pilots who understood the Jumo 213's quirks were dead, captured, or too valuable to risk in combat. Replacement pilots received minimal instruction on engine management. One Jagdgeschwader commander reported that 60% of his new pilots destroyed their engines through improper operation before encountering any enemy aircraft. Overboosting during climbs, shifting supercharger speeds incorrectly, or failing to monitor temperature gauges during sustained combat power settings that the engines couldn't survive without perfect management. Even tactical doctrine couldn't adapt. German fighter tactics evolved around the Bf-109's characteristics. The FW-190D with Jumo 213 required completely different approaches. The final irony came when Allied forces captured the factories. When American and Soviet forces overran Junkers facilities in April and May 1945, they discovered warehouses filled with Jumo 213 engines, complete technical documentation, and experimental variants testing even more advanced concepts. Allied technical intelligence teams seized everything: production tooling, metallurgical specifications, supercharger designs, fuel injection systems, and engineering reports detailing 5 years of development that Western engineers had been attempting to replicate based on fragmentary intelligence from captured aircraft and pilot reports that never told the complete story. The irony was profound. The two-stage supercharger technology that arrived too late for Germany became standard on post-war Allied engines within months. British and American engineers studied the Jumo 213's fuel injection system and incorporated similar designs into their next-generation power plants. Soviet engineers literally relocated entire Junkers production facilities to the USSR, machinery, documentation, and German technicians forced to continue working under new management, creating a direct technological transfer where Stalin acquired years of German research and development without investing a single ruble in the original development costs. The Jumo Tu-153 influenced jet engine development paths that German engineers never witnessed. Lessons learned from high-temperature metallurgy, precision fuel metering, and supercharger aerodynamics transferred directly to turbojet programs. American engineers working on the General Electric J-47 turbojet that would power the F-86 Sabre-credited captured German engine documentation, including Jumo 213 technical reports, with solving critical compressor design problems that had stalled their development for months, demonstrating how Germany's advanced aviation engineering ultimately benefited the very nations that destroyed the Luftwaffe. The engine that was supposed to restore German air superiority instead became the foundation for Allied post-war aviation dominance. Its technology seized, studied, and incorporated into weapon systems that would define Cold War aerial combat for decades. The Junkers Jumo 213 represented everything wrong with late-war German aviation. Brilliant engineering arriving too late, manufactured under impossible conditions, and operated by inexperienced pilots with insufficient fuel. Advanced technology couldn't overcome strategic failure and industrial inadequacy. The engine's greatest contribution came after Germany's defeat, powering Allied post-war aviation through captured documentation and seized technology. Watch the next video on vintage planes for more aviation truths.